So today I want to tell you about how densities of discrete random variables behave and talk about some measures of central tendency like the mode and the median of a distribution. As always, let's start with a story. As the army approached the gates, the king turned to his scouts and asked, "How large is the approaching menace?" The scouts huddled together and reported, "We're not sure, Your Majesty. However, we can say that the probability they number n,000 troops is 3 to the n times the exponential function at -3 divided by n factorial." The king sighed, wondering why he had hired scouts so invested in probabilistic modeling. "Just tell me," he pleaded, "can you give me the number that is most likely?" Densities for continuous random variables are with respect to Lebesgue measure, which is why to find the probability that x is in a set A when x is continuous, a Lebesgue integral is used. Discrete random variables also have densities, but they are with respect to counting measure rather than Lebesgue measure. For counting measure, think about what a little differential element from x minus dx over 2 up to x plus dx over 2 means. Consider a point y. The only way for y to fall in the differential interval is if y equals x, in which case a count of 1 is registered. Otherwise, if y doesn't equal x, a count of 0 is registered. The result is that the probability that x is in a little differential element A is the same as the probability that x equals A exactly when working with discrete random variables. Now consider how integration is performed against counting measure. For instance, consider the integral from 1 to 5 of x squared times the indicator x must be the integer 1, 2, 3, 4, or 5 with respect to the differential of counting measure. There are only 5 values of x where this differential is positive, at x equals 1, 2, 3, 4, and 5. The first value, x equals 1, has this differential of counting measure equal 1, so the integral gets a contribution of 1 squared, which is 1. The second value, x equals 2, also has the differential of 1, so the integral gets a contribution of 2 squared equals 4. Working towards 5 gives that s, the integral of x squared times the indicator x is in the set 1, 2, 3, 4, 5 with respect to counting measure is the same as the sum as I runs from 1 up to 5 of I squared. And so it's just 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, or 55. In general, integrals with respect to counting measure are a sum. If I let the number sign denote counting measure, then for a countable set A, the integral over little a in big A of f of a d with respect to counting measure equals the sum over little a in big A of f of a. For example, let x, which has the distribution of a d6, be the roll of a fair six-sided die. Then the density of x with respect to counting measure at I is 1/6 times the indicator that I is in the set, 1, 2, 3, 4, 5, 6. What is the probability that x is less than or equal to 2? Well, the probability that x is less than or equal to 2 is the same as the probability that x is either 1 or 2. And so we integrate for I in 1, 2, the set, the PDF of x at I with respect to counting measure. That turns into a sum. It's the sum as I goes from 1 to 2 of 1/6 times the indicator that I is in the set from 1 up to 6. When I equals 1, that returns 1/6. When I equals 2, that returns 1/6. We add them to get 1/3, which is about 0.33333. Now, an old term for the density of a discrete random variable is the probability mass function, which is unfortunately a terrible name that it makes absolutely no sense, because mass can either be concentrated in pieces or spread out continuously like creamy peanut butter. Still, the term is used now and then, so be aware that the density of discrete random variables is sometimes called the PMF, where the M stands for mass instead of the PDF. For a discrete random variable x, the density, aka the PDF, aka the probability mass function, aka the PMF, is the PDF of x at I is just the probability that x equals I. Now, turning a PDF into a CDF is the same for the discrete world as in the continuous world. The only thing to note is that the integral becomes a sum. So the probability that x is less than or equal to a is the integral from negative infinity up to a of the PDF of x at s with respect to counting measure, and we can write that as the sum for I less than or equal to a of the PDF of x at I. The fact that the CDF is a sum leads to the CDF having jumps. That is, the CDF is continuous for continuous random variables and has jumps when the random variable is discrete. For example, if you were asked to draw the CDF of x when the probability that x equals 1 is 0.2, the probability x is 3 is 0.5, the probability x is 5 is 0.3, well, the CDF of x will have a jump of size 0.2 at x equals 1, a jump of size 0.5 at x equals 3, and a final jump of size 0.3 at x equals 5. For the random variable with density f, we can then ask, where is the center of the distribution? There is more than one way to measure that, and these different methods are called measures of central tendency. Our first measure of central tendency is called the mode. We say that a random variable x with the density f sub x has mode m if m is an element of the argument maximum of f sub x of x. The set of all modes of x is the mode set of the random variable. So what exactly is the argument maximum? Well, if x is a discrete random variable, a mode x will satisfy the equation the probability that x equals little x is greater than or equal to the probability that x equals little s for all other s. If x is a continuous random variable, then a mode is any value x such that the probability that x is in the little differential element around dx is greater than or equal to the probability that x is in a little differential element around s for all other s. Now note that the mode might not be unique. In the story for today, the PDF of big N at little n is e to the minus 3 times 3 to the n over n factorial, and the goal is to find the mode. That is, what value of n makes this PDF at little n as large as possible. One way to find out is to consider the ratio r, which is the PDF of big N at n plus 1 divided by the PDF of big N at little n. When I plug in the formula, most of the terms cancel out, but I have a 3 to the n plus 1 in the numerator, a 3 to the n in the denominator. That leaves a factor of 3 in the numerator. The e to the minus 3 cancels out of the numerator and denominator, but I have n plus 1 factorial in the denominator of the numerator and n factorial in the denominator of the denominator. Those cancel to leave a single factor of n plus 1 in the denominator. Now, when r is bigger than 1, that means that the PDF of capital N at n plus 1 is strictly greater than the PDF of capital N at little n. So little n cannot be the mode of this expression. Similarly, when the ratio is smaller than 1, the PDF of big N at little n plus 1 is smaller than the PDF of big N at little n. Finally, if r equals 1, then the PDF of big N at n plus 1 equals the PDF of little n at the PDF of big N at n plus 1 equals the PDF of big N at little n. Now, in the problem, r is less than 1 if n plus 1 is less than 3, so n is less than 2, and bigger than 1 if n plus 1 is greater than 3, or n is greater than 2. And when n equals 2, it holds at r equals 1. So this tells us that n equals 2 and little n equals 3 are both modes of capital N, and there are no other modes. Now, the ratio method works exceedingly well when there are n factorial type of factors in the PDF, as they mostly cancel out as seen above. For continuous PDF, derivatives are usually the way to go when finding modes. Suppose that the PDF of x at little s is s squared times e to the minus 3s times the indicator s is greater than or equal to 0. And we're interested in what is the mode or modes of the random variable x. Well, when s is less than or equal to 0, the derivative of the PDF is 0. Now, consider the derivative of the PDF when s is greater than 0. We can use the chain rule to say that this is the derivative of s squared times e to the minus 3s plus s squared times e to the minus 3s, the derivative of that last term. So the derivative of s squared is 2s, so we get 2s times e to the minus 3s. The derivative of e to the minus 3s is negative 3 times e to the minus 3s. So when we factor out an e to the minus 3s, we get that the derivative is e to the minus 3s times s times 2 minus 3s times the indicator that s is greater than or equal to 0. The reason I factored out this factor of e to the minus 3s is that e to the minus 3s is always going to be greater than 0. Also, s times the indicator that s is greater than or equal to 0 is also going to be greater than or equal to 0 for all s. So when we have s strictly greater than 0 and 2 minus 3s less than 0, the derivative is negative. And when s is greater than 0 and 2 minus 3s is greater than 0, the derivative is positive. That means that the function goes up when 2 minus 3s is greater than 0, and then switches and goes down when 2 minus 3s is less than 0. This switch occurs at s equals 2/3, so the mode occurs there. And the unique mode for this density is 0.6666, etc. Now, another way to look at where the center of the function is called the median. Say that m is a median of a random variable x if both the probability that x is less than or equal to m is greater than 1/2 and the probability that x is greater than or equal to m is at least 1/2. The set of all medians of a random variable x is called the median set. Suppose that A is a D5. What is the median set of A? Well, A is the roll of a fair 5-sided die, and so for I in the set 1, 2, 3, 4, 5, the probability that A is less than or equal to I is I over 5. So to make the probability at least 1/2, we must have I greater than or equal to 3. Similarly, the probability that A is greater than or equal to I is 5 minus I over 5. So any median has to have I less than or equal to 3. The only number that satisfies I greater than 3 and I less than 3 is 3. And so that is the unique median of this random variable. For discrete random variables, the median set can contain more than one value. So now let's switch to a fair 6-sided die. Let B have the distribution of a D6. Well, if I'm thinking about a real number A that's greater than or equal to 0 and less than or equal to 6, the probability that B is less than or equal to A is the floor of A divided by 6. In order for that to be at least 1/2, we have to have I greater than or equal to 3. Similarly, the probability that B is greater than or equal to A is the floor of 7 minus I divided by 6. So any median must have I less than or equal to 4. So we know that any median for this random variable b has to be at least 3 and at most 4. Well, let's pick a value I in this interval from 3 to 4. Well, the probability that x is less than or equal to I is at least the probability that x is less than or equal to 3, and that's 1/2. And similarly, the probability that x is greater than or equal to I is greater than or equal to the probability that x is greater than or equal to 4, also 1/2. So not only does a median have to be in the set from 3 to 4, any value in the set from 3 to 4 is a median. And so the median set is the set of real numbers from 3 up to 4. When a constant is added to a random variable, that is called shifting the random variable. Multiplying a random variable by a constant is called scaling the random variable. How that affects the density depends on whether it is applied to a continuous random variable or a discrete random variable. Let a be a non-zero real number and b be a real number. X be the random variable with PTF f sub x, and y be this shifted, scaled version of x, a times x plus b. If x is a continuous random variable, then the density of y at s will be 1 over the absolute value of a times f at x evaluated at the quantity s minus b over a. If x is a discrete random variable, then the density of y at s will be f at x evaluated at the quantity s minus b over a. The difference is the discrete random variable doesn't divide the density by absolute value of a. So why the difference between continuous and discrete? Because in the continuous world, for y equals ax plus b, that transformation, the differential of y is a times the differential of x. While in the discrete world, with respect to counting measure, dy and dx are equal. Or you can just think about the proof. The proof goes as follows. Let x be continuous. Then for a greater than 0, by the chain rule, the density of y at s is the derivative of the probability that a times x plus b is less than or equal to x. Solving for the random variable x, that's the derivative of the probability that x is less than or equal to the quantity s minus b over a. And then using the chain rule, that's going to be the density of x at s minus b over a times the derivative of s minus b quantity over a, which is just the density of x at s minus b over a times 1 over a. Now, on the other hand, when a is less than 0, we can work through that exact same computation, but because we multiply by a negative number inside the inequality, the order of the inequality switches, which means that we end up with the density of x at s minus b over a times 1 over negative a. We want to write both expressions using one sort of notation. We can say that the density of y at s is the density of x at s minus b over a divided by the absolute value of a. Now, for discrete random variables, it's much simpler. The density of y at a is just the probability that y equals a, or that a times x plus b equals I, and solving for x, we get equals I minus b over a, so it's the density of x at the quantity I minus b over a, and we're done. Suppose that t is exponential with rate 1, a standard exponential. What is the density of 3t plus 4? Well, the density of t is f at t at s, which is e to the minus s times the indicator that s is greater than or equal to 0. Plugging in little s equals t minus 4 quantity over 3 gives that the density of 3t plus 4 at little t is 1 over the absolute value of 3 times the density of t evaluated at t minus 4 over 3. That's 1/3 times the exponential function at minus quantity t minus 4 over 3 times the indicator of the quantity t minus 4 over 3 greater than or equal to 0. Well, let's look at that indicator for a second. The indicator of t minus 3 quantity over 3 greater than 0 is the same as the indicator of t greater than or equal to 4. So we can simplify that considerably. Inside the exponential, we can keep the e to the minus t over 3 and bring the rest of the exponential outside to have exponential of 4/3 divided by 3. Now suppose that x is the roll of a fair 3-sided die. What is the density of -2 times x? Well, here x is a discrete random variable. So the density of -2x at I is the density of x at I divided by -2. So we have the 1/3 coming from the fact that x is uniform over 1, 2, 3 in the density. And then we have the indicator that I over -2 has to be in 1, 2, 3. When we solve inside the indicator for I, we get the indicator I has to be in the set -2, -4, -6, and the divided by 3 comes along for the ride, giving us our final density. If an item lasts capital T time before breaking, then if capital T is greater than little t, that means that the item has survived past time t. This motivates the definition of the survival function of a random variable. The survival function of a random variable is 1 minus the CDF of that random variable. So the survival function of x evaluated at t is the probability that x is greater than or equal to t. And that's a nice complement to the CDF function that comes in handy in some applications. So that's how you handle densities of discrete random variables. See you next time.